Hi, my name is Rachel Moffett. I'm in Engineering Materials 201, and my topic is on dislocation motion. So first we're going to discuss what dislocation motion is, just briefly. Dislocation motion enables atoms and metals to slide readily by one another, facilitating the plastic deformation that blunts the advance of cracks. So just a continuation on from this, it is a linear crystallographic defect or an irregularity within a crystal structure that contains an abrupt change in the arrangement of atoms, and that can be seen in the image down below. The movement of dislocations allows atoms to slide over each other, like I said, and this can be known as a slip. So to understand dislocation motions, you're going to have to understand slips. A slip is the large displacement of one part of a crystal relative to another part along a crystallographic planes and directions. So it's when objects are basically sliding past each other. Slips occur by the passage of dislocations on close packed planes, which are planes containing the greatest number of atoms per area in the close packed directions. And that can kind of be seen in the image below. That image has a few slips in it. So next, I'm just going to describe what's happening and why dislocations occur. They can occur because of a response to stress, slip systems, and plastic deformation in single crystals and crystalline materials. This can be used as a strengthening mechanism. So strain hardening would be a ductile metal becomes harder and stronger as it plastically deforms. And the grain size reduction is another factor, and this increases grain boundary area, more barriers to dislocation motion, and increased yield strength, tensile strength, and hardness. So just some examples of dislocations are edge and screw, and these are two very popular ones that are most often seen. So edge dislocations move in response to shear stress applied perpendicular to the dislocation line, and that can be seen in the image based off where the arrow is pointing for the direction of motion. As the dislocation moves, its extra half plane will break the existing bond and form new ones. So you can see the before and after in that image. And compare it to the screw, it is the opposite. You can see in this image the direction of motion is facing a different way, and you can see how that object has been, or material has been affected by its direction of motion. So hardness and strength are related to how easily metal plastically deforms. So by reducing dislocation movement, the mechanical strength can be improved. So as opposed to that, if dislocation movement is easy, the metal will be soft and easy to deform, which I'll go into later detail right now. So dislocations in metals. The dislocation motion in metals is easiest, which means it's going to be softer after the process. So it's because it has non-directional bonding and the planes are closely packed together, and it has directions for slips. And like earlier, it was said that slips can occur and cause dislocation motions, which is why it's going to be easiest for metals because slips occur more often. So some examples of metals would just be steel, copper, iron, and many others as you can name. So you can see in the image the type of packed bonding that metals have. So dislocation in covalent ceramics is going to be a little bit more difficult because of the bonding. So these are going to be your diamonds, graphites, and so on. And the dislocations in ionic ceramics will also be difficult because there are a few slip planes and there's not really room for dislocations to occur. So this will be some examples down here. So in conclusion, dislocation motion is needed in order to strain harden and reduce the grain size of materials. And we also learned that the easier the dislocation movement, the softer the material. And so from easiest to hardest would be metals, covalent ceramics, and ionic ceramics. Thank you so much.